All right, so let's get started. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for today. I thank you for these students. Pray that you help us to use this time wisely to prepare for the test tomorrow, Lord. In your name I pray. Amen. So by now you have gotten your mission 8 back with its very careful grading. Alex? Aha. So, yeah, if you made mistakes, sorry, I didn't point them out to you. I unfortunately do not have time to grade a homework in here, so I rely on the grader. And, well, as you can see, well, I guess you're happy that they're not reliable. Let's see here. So,
wait, can I ask if you gave us 30s because you were lazy or because your grade was lazy?
who was lazy? I don't know. I mean, I do pretty much nothing but math when I'm awake. I don't think I'm the lazy one, but. What's that? Now, I will say this. I send an email casting doubt upon an integral in problem 116, was it? 113. I do think the integral I have there is right. I reworked it, and I got the same answer again. So I think that the integral is fine as it stands. So for what that's worth. Okay, so any questions about quiz 4? Let me just get on with it. What's this quiz about? I mean, what's the quiz about? What's it? Excuse me. What is this impending exam about? What doom befalls you tomorrow? Let's see here. Where are we? Test 4 looks like vector fields and the gradient operator, line integrals, conservative vector fields. Ooh, I love conservative vector fields. Green's theorem, you probably forgot about that. It still matters. Surface integrals, Stokes' theorem, Gauss's or divergence theorem. And the stuff on Green's identities and the Helmholtz theorem, I'm not likely to put on the test. Perhaps I might have a token question on the final, but that would be it, okay? And the differential form stuff is, I don't think I'd put that on the test. I mean, we'll have plenty to do tomorrow without me testing wedge products and differential forms. So don't worry about that. If I
Don't worry about what?
the wedge products and differential forms is stuff I did Friday. I might put a bonus question on the final, just to reward those of you who take a minute to work on it. But so that's a quick overview. Now, do you guys have any specific questions about where to go? Sorry, I'll get with it eventually here. Any questions about quiz 4 or just generally how to approach things? Yes?
Something like problem 2 on quiz 4 about how to think about conservative vector fields.
So how to think about what was that? There's the blasting. First of all, this calculation I did right here, is it necessary or unnecessary?
I did that in my head because someone gave me that. That's what I got.
I mean, you also got there. My question though is there an easier way to do this problem?
I'm going to say yes because you're.
I'm just asking the question. I mean, I don't really know. If it were in fact the case that this was the gradient of some potential function, right? And if this curve is from, say, point A to point B, then this would be f of b minus f of a, right? That is easier, if you can find the potential function. But you can't always find a potential function. And for this one, we could calculate the curl of f. What's the curl of f going to be? I mean, I think that this has non-trivial curl because there's a z in the x component, and there's an x cubed in the z component. I don't think those are going to cancel. So if you look at it, like the x hat component is 0, the y hat component is 1 minus 3x squared. The z hat component is 0. Well, as you can see, this is not equal to 0, right? If the curl is not equal to 0, it's not conservative. Good news, Mike, you did not waste your time. That was, in fact, the only way to do this problem. I mean, modulo breaking it into a Riemann sum and formally calculating the limit. Yeah, only a really stupid person would do that. Somewhere, some numerical methods person is like, how dare you? That's how they calculate things, breaking it into pieces and actually doing the Riemann sums. Anyway, so problem 2, what Zach was asking me about like a minute ago. Suppose C2 is another path, all right? Check it out. I just calculated that. Great. The curl is non-zero, right? So f is not path independent. It follows that the value of the integral, the line integral along a different path could be different. It could be the same. I don't know. I can't say much more, right? What was our list of equivalent conditions for conservative vector fields? Do you remember? We had 4. So first of all, the definition. Let's say R3. F is the gradient of f on R3. I'm going to turn the light. Is it picking up or? I'll turn the light back on. People can always look at the PDF for this. The other one was that the integral over C1, integral over C2, for all C1, C2, like this. So here's the set U. So the following are equivalent. These are equivalent statements. These are the different ways we have to look at a conservative vector field. So this is the definition, the first one. Conservative on U. And I'm just talking about R3 for the sake of specificity. What was the other? The equivalent to this was the integral around loops is what? Right? And our fourth and more technical condition was if you simply connected curl of f equal to 0 is also an equivalent condition. But you need simple connectedness in order to make this equivalence. So without qualification, only 1 through 3 are equivalent. With the extra data that the set we're considering is simply connected, we can throw in 4. However, you always have that the curl of a gradient is 0. So f conservative always implies that the curl of f is equal to 0. That is without regard to the simple connectedness. That's just an identity of differential vector calculus. But to reverse it, I have to do Stokes' theorem on an arbitrary surface, and then for that I need the simple connectedness in order to apply Stokes' theorem. Does that answer your question, Zach? So there's these four different ways of looking at when a vector field is conservative. But kind of the more basic thing beneath all this fancy talk is I just first thing I do is just kind of look at it and do some educated guess. And if I've got x, y squared, z to the 4th plus 7, I just go, hey, that's the gradient of 1/2 x squared plus 1/3 y cubed plus 1/5 z to the 5th plus 7z. And I'm like, okay, so it's conservative because I can guess the potential function. When there's mixed terms, then we have to do the algorithmic thing and make sure that we've not double counted stuff, but yeah. You must understand all 4 and their interrelation. So you'd like to be able to prove that 1 implies 2, and 2 implies 3, and 3 implies 4. I mean, that's the highest form of studying in here. Some implications are harder than others. For example, I think this implication is the trickiest one. That 2 implies 1. That's the one we had to say, okay, we have path independence. We wrote down h is equal to the integral from a fixed point to another point, and then we showed the derivative of h with respect to x actually picked back up the x component of the given vector field. So the proof that path independence implies the existence of a potential function is the most subtle aspect of that equivalence, I think. But in my opinion, I mean, to get between 2 and 3 is easy. These make actually pretty good test questions. Like, suppose you have path independence. Can you prove loops are 0? Suppose you have this for all, for all paths. With matching terminal points. All right, same beginning and ending points. Oh, I'm sorry. Now, how do you show that that implies that the integral around a loop of f dot dr is equal to 0? How would you prove this? Right, you say assume. I mean, it's a usual if-then proof. You assume what's assumed, right? Suppose this is true, and then you just consider what you're trying to prove, right? Look at an arbitrary loop like that. You said pick 2 points and loop whatever 2 points you like, right? Like this point and that point. And just take your loop and divide it up into, there's 2 curves, say C1 and minus C2, right? And so that this then tells you the integral over C1 union minus C2 of f dot dr is equal to 0. But in properties of the line integral, that says the integral over C1 of f dot dr plus the integral over minus C2 of f dot dr is equal to 0, which then tells me, of course, the integral over, oh man, I'm an idiot. I got turned around and backwards. So sorry. So you're trying to show the loop is 0, right? So you take the loop and you divide it into 2 curves, C1 and say C2, like that, right? Well, maybe I should call it, give them different names. How about the loop is, C what? C Bob? C Lucy? Yeah. Okay. I haven't used Lucy in here yet. I'll take it. So this would then, this would be equal to the integral of what? Over C Bob union with C Lucy of f dot dr, but more to the point, it's the sum of C Bob and C Lucy, right? And then, but this is the integral over C Bob and then minus the integral over minus C Lucy, right? And the reason that that's equal to 0 is because C Bob and minus C Lucy are 2 curves that have the same terminal points, and we are assuming that those are equal, so these cancel and give you 0. Sorry, I am having trouble communicating this today, but it's also in the notes, and it's I mean, like I said, the equivalence of 2 and 3 and too hard to prove. Of course, my primary goal for you is to be able to use this equivalence to solve problems, right? So I'm talking about the second order part right now. How about problem 3? F is e to the x, y e to the y squared, 3z squared. Is this a conservative? Well, I mean, as a general rule of thumb, right? If you have x is the x has an x dependence, y has a y dependence, z has a z dependence, that's the easiest case. You can just integrate them kind of in isolation, and that will be the potential, like I just did in that silly made-up example over there, right?
Or just integrate them individually, add them up
Exactly. Yeah, that's what I meant. Integrate them individually and add them up. Exactly that. So e to the x, 1/2 e to the y squared, and z cubed is the integrals. So you mean I still have to know how to integrate? Yeah, still true. Sorry, I do insist on integration. I still haven't gotten around to testing your partial fractions decomposition, have I? And the trig substitution. We haven't gotten back to the trig substitution enough in here yet, have we? Oh no, you should let that be? I can trust you? You're good on that? Oh, okay, just checking. You guys are like, I have 5 other tests this week. Now is not the time for this. Projects, those are supposed to be done over the course of the semester, not in the final week they're due. Sorry. That was almost as good as the email I got earlier on the title of a new course. I shouldn't really tell you this, guys, but I'll tell you. So we're starting this new course. It's like something below pre-calculus, like something kind of, it's like just a little bit below pre-calculus, but not exactly. And I think we're going to end up calling it Advanced Technical Mathematics. Isn't that fantastic? I love it. I love it. I want to teach Advanced Technical Mathematics, yeah. No, I probably shouldn't. I have enough trouble keeping the trigonometry out of business calculus. I mean applied calculus, whatever it's called. Almost calculus, as some student calls it. I wouldn't call it that, of course. That's offensive. You wouldn't catch me calling it almost calculus. Of course not. It is a good course. I do like 126, actually, in its way. So I think you guys, you'd be like, you better put a divergence on this test. This is a new thing I learned, and I should be tested on it, right? Okay, you're like, and I like to be tested on it in Cartesian coordinates, please. Yeah, I thought so. All right. I probably will have some token question somewhere on the non-Cartesian stuff, but it shouldn't be the whole test, you know. Anyway, so the curl of f is another thing you should be able to calculate, right? Now, there is a faster way to go through this, right? If you already had recognized that this f is the gradient of some potential function, then you could just say the curl of the gradient is 0. But I guess I don't see it right off. Is this conservative?
If you put the y in there, but it's not there on the blank.
Oh, I
So
see,
it's
I
a
see.
little tricky when-
Yeah. I think I added the y during the test, and then I never went back and fixed my original file.
But it was fun doing.
It was fun without the y? Yeah, without the y, it's not conservative. Okay. So without the y, this question's very boring.
Well,
Or
it is pretty interesting about the
I guess without the y, there's no c. Right?
Yeah. C is very, but B becomes.
But that's actually important. I would be so delighted if the majority of you understood when is a vector field conservative, when is it not conservative, and what does that tell you about the vector field. That would be a huge victory for me if most of you understood that leaving here. Please do. Any questions about this? So, line integrals are so much more fun when you know the potential function, right? So, let C be, don't forget, we talked about the flux through a curve, right? And the line integral along a curve. Those are two different things. How do you calculate the flux through a curve? In other words, f dot n hat ds, where s is the arc length. What was the formula for it in terms of dx's and dy's? Do you guys remember? That is something that should certainly be on your formula sheet, right? How do you calculate the flux through a curve just directly? This had to do with the discussion of the divergence form of Green's theorem, remember? So like I said, f dot n hat ds. But what's the formula for it in terms of dx and dy? I suppose f is p comma q as usual. What would be the formula? I mean, here's 50-50. P dy minus q dx. Am I right or wrong? Right? I mean, I really don't know. I'm asking you guys for confirmation. Yeah. I mean, the way I remember is to look at a little picture, doo-doo, and then convince myself, what's the little n hat look like, you know? So apparently n hat is dy ds minus dx ds. Let me make sure this makes sense. If I'm here, the normal should be like that, right? And if the curve is like so, dx ds is negative, dy ds is 0, so it's 0 this way or that way, and it's up, right? Down here, dx ds is positive, but it should be directly downward. Yeah, okay, that's right. And so if you take this and you dot it with p comma q, you get the formula above, right? The ds's cancel. In contrast, right, the work done by the vector field along the curve is the integral of p dx plus q dy, which is a different integral, right? These are not equal. They describe different things about the vector field along the curve. One gives you the work done, the other one gives you the flux of the vector field through the curve. There's no reason they should be equal. Now, was there a question that I ignored just a second ago? Or do you have a question to ask her? Now, that said, the way I actually did this problem was to use the divergence form of Green's theorem because it's easier, right? To actually calculate the line integral, I don't know, it just seemed like more trouble. So I used the divergence form of Green's theorem, which says that this is equal to that. And then I just have to integrate this, and they go, aha, polar coordinates, this is 3r squared. But I've got an rd theta from the dA, which gives me this integral, which gives me that. So of course, you should be looking to use polar coordinates where you can. And often the domain is kind of an indicator, right? If you've got a disk, maybe you should be thinking about polar coordinates, right? If you've got a cone, maybe you should be thinking about spherical coordinates. If you've got a cylinder, maybe you should be thinking about cylindrical coordinates. If you've got a sphere, probably should be thinking about spherical coordinates. There are exceptions, but that's a lazy Pac-Man right there. I was trying to, it's like, what's that? You hope I have a Pac-Man on this one? Or Pac-Girl? How hard is it? Like, it's not, I mean, not too hard, but, I mean, to draw a new one? Well, this one is carefully drawn. I mean, I don't know. See, the thing is, I have to have a picture file already there to include in the thing. I don't deny there's a laziness here. Okay, any questions about this? What did I do? What did I use to calculate it? I didn't, first of all, why didn't I just integrate the line integral directly? Because it'd be like a circle and two lines. That's three separate integrals to do, right? It's a pain. Or I can do one area integral, which in polar coordinates isn't too bad. So I use Green's theorem to convert this integral And why can I do that? Because this is a simply connected region and the Pac-Man is its boundary. Simple closed curve boundary, right? And there it is. So I end up with the integral of r squared dA, which is r cubed dr d theta. Oh man, these are kind of boring. We just did r cubed dr d theta in the one above. Well, okay, but I mean, fine. Fair enough. Yeah.
Well, okay, say you wanted like boundaries for theta. You wanted them to be either pi over 6 or pi over 6. Could you do 2 pi minus that?
Could I do? Well, I mean, I subtracted pi over 6 from 2 pi to get that there. I mean, in the picture, I've got minus pi over 6. In the integral, I've got pi over 6 to 11 pi over 6, right? I mean, alternatively, I'd have to, like, split it into 2 pieces, integrate from, I don't know. It's unfun. You want to pick a connected domain of theta, which gets the whole thing, and not be a stickler for using theta that are specifically between some range. Like that's a losing proposition, except for simplicity of certain definitions. In actual calculations, you want the freedom to choose whatever theta makes sense geometrically. I think this is just a plain old calculation. There probably will be one of those on your test. There's probably going to be some problem somewhere where it's not a trick. It's just you do the calculation. So here, I mean, probably the cosh squared is going to go away because of something, but yeah, because the normal has a 0 component, so the cosh squared goes away when you take the dot product of f with ds. But I mean, how am I calculating this? I gave you the parameterization. Calculate the normal vector field. Take the dot product of the normal vector field with the force field that you're given. Evaluate it at the parameterization, right? Which is this. And then you got to integrate this over what? Over the appropriate range of parameters, which in this case is a square. I don't know if there's any. I'm trying to think. Is there any way we could shortcut this calculation using a theorem? I tend to think not, because what this is just some kind of like patch, right? It's just some kind of like whatever over the square 0, 1, 0, 1 right here, right? So like this is the parameterization. It gives you the surface S, which is just some like basically patch on a quilt. It's not connected. It's not like bounding some region or something. I can't use the divergence theorem, right? So pretty much just direct calculation is all I can hope for here. Now, if you're asked to calculate the flux through the boundary of a simple solid, then your mind should immediately go to what? Like this one. Find the flux of this vector field through the surface of the positively oriented cube. This is a totally different animal. The cube is a closed surface, right? There's no boundary to it, and it's encapsulating the cube, right? So that I can apply the divergence theorem to. So thankfully, I don't actually have to calculate those 6 surface integrals separately, right? There are variations on this theme, right? I could ask you to calculate the flux over 5 faces of the cube. Then what would you do? What's probably a good strategy if I were to ask that? What if I said, calculate the flux over everything except for this face? How would you handle that problem? Yeah.
I try to take a flux through the whole thing if I would get here, and then subtract the flux from one face.
Right. Exactly. Use the divergence theorem to calculate the net flux, then calculate the flux through this one face explicitly, directly, in the style of the previous problem, and subtract it from that, and that would give you the flux through that one face. And that's a savings of 3 integrations. 1 volume integration, 1 surface integration versus 5 surface integrations. Yep. Is it 7/4? Where? You're saying that my calculation here is wrong? It is possible. I mean, what? Oh, I should get a 4u minus 2u cubed plus u cubed. Ah, so yeah, that 2 should be a 4. Yeah. I agree. So this should be a 4u, which makes this a 4u, which makes that so 4u. And would make that 2 minus 7/4. Yes, totally agree. 7/4 is the right answer here. Yep.
This might be a dumb question, but how do you calculate the flux with the one flux?
Oh, sure. So, not at all a dumb question. And that's really, it's been a little while since we did this, but remember, before we talked about the Stokes theorem and the divergence theorem, we first talked about what's the definition of a surface integral, right? So to calculate the surface integral through, say, this particular side of the cube, right? This one right here. To do that, I have to figure out a parameterization, and I have to figure out ds. Now here I argue that to figure out a full bore parameterization is not really needed. We can see from intuition and geometry what ds should be. ds, so if this is, if this is the x direction and this is the z direction, right? First of all, it's in the y hat direction, right? It's put in that direction. And then if I think about a little square right here, surely that should be dx dz. Do you agree? Then the question is the details of the cube. What kind of cube am I looking at? 0, 1. So the equation of this is actually y equals to 1 and 0 less than or equal to x comma z less than or equal to 1, right? So to calculate the flux through that particular face, I have to say f dot ds. I need a face. What do you want to call this face? We'll just call it face. There you go. Integral along that face. And what was my vector field? Ugh, this thing. So let me put one more intermediate step, okay? Maybe not. So integral from 0 to 1, integral from 0 to 1, and I take that vector field formula, right, and I plug in the formula for the face. The formula for the face is really boring. It's y equals to 1, x and z are left alone, which gives me x, 1, z. Now, I have to dot that with what? Y hat. Oh man, this is really... I should have asked the question this way. This would be much more interesting, huh? I mean, this is 1. Right? And yeah, the whole thing's 1. So the flux through the right face is 1. And so in view of the fact that the net flux out of the cube by the divergence theorem here is 5/3, you could tell then that there has to be what? 2/3 through the other 5 faces. So the flux somehow gets spread over all the different faces of a simple solid. wouldn't say that's a second order idea. Maybe that's like a 1.5 order idea here in this material. I don't know. Find the flux of the vector field f, x, y, z, through the boundary of the simple solid E, which is bounded by x squared plus 1, z equals x, and z equals 4 minus y. Usually students have a lot of trouble with this problem for some reason. I'm not actually sure why. I don't think it's that bad. But anyway, if you found this problem challenging, you have lots of good company in previous years. But basically the idea here is, first of all, I've got a cylinder, right? And I've got two z equations, right? So you should probably immediately gravitate towards the idea, as I set this up, I'm going to end up using cylindrical coordinates at the end for the integrations probably, right? And I should be thinking in cylindrical coordinates in terms of the geometry. So, you know, if you think about x squared plus y squared equal to 1, a useful thing to notice, x and y can be at most 1, and they can be at this absolute smallest minus 1, right? So as you're thinking about what are the possible values that z equals x could take on, think about it. X can be at most plus or minus 1 inside the unit circle, right? So x, the z equals x, bounded between plus and minus 1. Z equals 4 minus y. That is bounded between 3 and 5. So which one's on top and which one's on the bottom? Z equals 4 minus y is on top. Z equals x is on the bottom. And there's no chance that they intersect. If they intersect, it means I got a typo in the test, all right? That's what it means. There's never been a Calculus 3 class that has angered me so much, or just angered me. I mean, you guys don't anger me. I don't mean to misspeak. I mean, let's say a Calculus 3 class that had so expounded their love of cats and left-handed people that they drove me to write a problem with intersecting, no, I mean, this is bad enough. I will try to make the top and the bottom not intersecting. So we have a simple solid to work with, right? And once you have that, then you can apply the divergence theorem, which says that the flux through the thing is equal to the integral of the divergence over the volume, which is easy enough to set up in terms of cylindrical coordinates down here, right? Bottom z, top z, r goes from 0 to 1, theta goes all the way around, full sweep. And the divergence of this thing is 3. It's not too bad. I mean, in principle, the divergence function could pick you up some other thing to integrate, right? Maybe I could make the integral easier if well, maybe not. So here is a failed attempt at me trying to do this problem with the sphere. Like I have, at various points, I've tried to create problems which allow you to use Stokes' theorem or divergence theorem to do part of a surface integral or part of a line integral in an easier way by trading it for a volume or a line integral. This is an attempt at that, which kind of didn't quite work out right. Anyway, everything here is 0. So I know we're almost out of time. Ooh. Hey, that looks like fun. I guess I probably should. We did spend some classes proving these kinds of identities. I probably should ask you one of these. What? That's a good idea? No, not a good idea? You guys don't like identities? Yeah. Oh. Yes?
Last check test 4 from last year, was it listed? Are you going to post that?
No. I think this is good to look at, and there is other old tests to look at. I mean, I know you're just asking, but how about this problem here?
Wow. Great.
So here I have the modified problem is supposed to have without the square root, and you're supposed to calculate the line integral around that curve, which I have pictured. And And the dotted curve was a hint. The hint is that you don't have to calculate around that awful curve, because this vector field is conservative between the outer curve and the inner curve. So you can use the deformation theorem. It says the integral around the inner curve is equal to the integral around the outer curve because the curl is 0 in between. That's another theorem that you should definitely be aware of. The deformation theorem is such a huge resource in the calculation of line and surface integrals also. There's a deformation theorem for surfaces if you have two simple, like if I had some other blarg surface that somehow enclosed the cube, you can imagine, right? If the divergence of f was equal to 0 between the cube and the blarg, the flux through the blarg is the same as the flux through the cube. Now, if the divergence was non-trivial, you could add field lines or take them away, dependingly on the divergence. But if the divergence is 0, the flux stays the same. Yep. Yes, because that's this circle integral, which you can do. It's kind of bad form to show you the tricks before I show you the test, but oh well. I suppose you, I mean, you could say I remember that this integral is 2 pi if you want, I suppose, and I might give you credit for it. Let's see here. Were there other old resources for this test? I just posted missions 8 and 7 from your current semester, right? I usually look at your homework when I think about the test. And if you look at, oh, you said quiz that's not posted? Well, the other place you can look for old tests if you want, it's kind of scary to go back up in here. There's this multivariate calculus archive at the top. See that? I guess you probably don't see that. It's tiny. See up here, multivariate calculus archive? Click that thing. I've got oodles and oodles of tests from ages ago. But you know what? Calculus 3 today is the same as it was 5 years ago, 10 years ago, whatever years ago. If you go back far enough, some of these, that is true, but I'm a Platonist, so I believe that the theorems already existed.